Ice batteries take aim at peak energy demand. As the energy grid faces mounting pressure from rising demand and inconsistent renewable supply, commercial buildings are revisiting an older but increasingly viable solution: ice-based thermal energy storage. Ice battery systems function by freezing water during off-peak hours, typically overnight when electricity rates are lower. The stored cold is then used during the day to reduce air conditioning loads, effectively shifting energy usage to off-peak periods without impacting building operations or occupant comfort. At the heart of this resurgence is research from Texas A&M University, where Dr. Patrick Schamberger and his team are working to overcome the technical limitations that have historically constrained these systems. Their focus is on developing advanced phase change materials, specifically salt hydrates, that are designed to store and release thermal energy at more precise temperatures. These engineered materials aim to improve the efficiency and reliability of ice battery systems. A critical challenge has been phase segregation, which occurs during repeated freeze-thaw cycles and can degrade material performance over time. Schamberger's work, recently published in the Journal of Physical Chemistry, investigates how to prevent this degradation by improving thermal consistency and structural stability across decades of operation. We don't want to solve grid problems by building more power plants. That's a very costly solution, and they'd have to charge higher rates overall. In addition to increased reliability, the integration of materials with more controlled thermal characteristics opens the door for broader HVC applications, including potential use in heat pump systems for both heating and cooling. Reducing grid strain and operating costs for commercial properties. From a business standpoint, ice batteries offer more than energy savings. They present a scalable demand-side management tool for commercial building operators. Facilities equipped with ice storage systems can dramatically reduce their reliance on expensive daytime electricity. During peak periods, utilities often charge significantly higher rates, sometimes 40 to 60% more than off-peak pricing. Ice battery systems sidestep these costs by shifting cooling-related energy consumption to nighttime hours, automatically balancing loads without manual intervention. Grid flexibility is another key advantage. As utilities increase renewable energy penetration, the ability to shift consumption away from peak times helps stabilize overall grid performance. Rather than requiring utilities to invest in new generation infrastructure to meet short-term demand spikes, ice storage helps flatten demand curves using existing assets. This dual benefit, operational savings for building owners and grid stability for utilities, is driving renewed interest in deployment. Systems are already being used in large commercial buildings, including the 30-story 11 Madison in New York City, where they help manage HVAC loads in a dense urban setting. Even with current technology, systems are delivering tangible returns. But researchers believe the next generation of ice batteries could operate autonomously for decades, with seamless integration into existing mechanical systems. The path forward depends on continued material improvements, especially in resolving the long-standing durability issues caused by phase instability.